Section 2.5, Inverse Functions, Exponentials, and Logarithms. In this section, we'll consider a little bit of reality. Function f is a rule that assigns an output y to each input x. So we can express the function f in this form: f of x equals y. So a function is a set of actions that determines the system. However, in reality, it's often the case that the equation must be solved for either the input or the function. There are three kinds of problems in the world. And here, out of these three, f, x, and y, two of them can be given. Once f and x is given, then we have to get y. Getting y is the simplest and most common task in the world. And f and y can be given, then we have to find x. Solving for x is to find the inverse operation of f. Now, finally, x and y can be given, then we may try to find f. Solving for f is not a simple task in practice. And now, even though you find some f, it is not really exact one. It is an approximation in most cases. To find the f, we may try to use many data points, and xi, yi. Finding an approximation of f is the core subject of polynomial interpolation, regression analysis, and machine learning. We'll consider this subject later on. Here we have a question: what is the inverse of a function? A function is defined on x and y is codomain. Now, for simplicity, we consider this function. F of x is 2x plus 1. Then, f is a rule that performs two actions. The first one is multiplication by 2, and the next operation is adding 1. Its reverse must be here. First, subtraction by 1, followed by division by 2. So here, if we start from y, then the reverse of f can be written in this way: subtract 1 and divide by 2. And if we call this the g of y, then g of y is inverse function of f. However, it is conventional to choose x for the independent variable so that we interchange x and y. So from here, we get that one. So x minus 1 over 2 is g of x. This is the inverse function of f given here. We can summarize this computation in this way. For y equal f of x, we first solve for x, and we have the inverse function and with independent variable y, and we exchange x and y so that we reach at the conventional inverse function. Okay. Inverse functions. The first step for finding the inverse function of f is to solve y equal f of x for x, and we'll get x is g of y. Here the required is for g to be a function. For to satisfy this requirement, and we need some requirement for the function f. Function f is called a one-to-one function if it never takes on the same value twice. That means that here, once x1, x2 are different, then their image cannot be the same. Then the function is one-to-one. Now, the one-to-one property can be checked by using horizontal line test. A function is one-to-one if and only if no horizontal line intersects its graph more than once. I guess you learned it from high school already. I'm sorry. Check if the function is one-to-one. Okay, let's try to check it. Now, A. Okay, let's start with A. Now, y called fx will make the graph in this way. I call it like that. So that if you are using horizontal line, then here the horizontal line will twice the graph. That means that this value, that value, okay, if this is x1, x2, then f of x1, f of x1, f of x2 are the same value, and here the height is that one. So that now this condition is broken. So it's not one-to-one. And from the horizontal line test, we see easily the line, horizontal line here intersect the graph twice. Now in B, if we restrict only non-negative part, then here any horizontal line will meet the graph only once, so that this is one-to-one. Right? Now how about that one? And y call here x, okay, h of x as x cubed, then the graph of this function is given in this way, is coming in this way, and like that, so that if you draw horizontal line, then every horizontal line will intersect the graph only once, so it is again one-to-one. Okay. Let f be a one-to-one function with domain x and range y. Then its inverse function has domain y and range x, and defined by in this way. Here, f of x, y is basically here can be written along with f inverse, applying f inverse. That can be x, and now the other side must be f inverse of y. Okay. Now here, and usually we are changing x and y so that we consider x as the independent variable. Okay, here let's see this function y called x cubed plus 2. Now to find its inverse, solve it for x, and then we reach that one, and now exchange x and y. Then here we have this one. So that if we put together, now that is f graph, that is f inverse graph, then we can see easily this is now deflection about y equal x. Okay, so because of this exchange x and y, the graph of inverse function is always here the symmetric in this way. Okay, deflection with about the line y equal x. Okay, now here we'll consider exponential functions. Exponential functions is in this form. F of x is a to the x. A must be positive and not 1. Once a is 1, then it's too trivial. So that a is not 1, and then a is positive. Then such function is called exponential function with base a. Now, exponential functions have a domain minus infinity to infinity, so it can be defined whole real line. Now, range is positive from 0 to infinity. Here, so all exponential functions are either increasing when a is larger than 1, or decreasing when a is between 0 and 1 over the whole domain. For example, there is a 10 to the x, then it's always increasing 10 to the 3x and 10 to the 2x. Now that is now here y equal 1 over 10 to the x. So it's written 10 to the minus x. That's the same as 1 over 10 to the x, and 1 over 3 to the x, 1 over 2 to the x. So that is the case where a is between 0 and 1. This is case when a is larger than 1. Okay. Now let's see this example. In the left side, the table shows the data for the population of the world in the 20th century. This is a real data. And figure 2.8, this right side figure shows the corresponding scatter plot. And time is measured from 1900. For each 10 years, the number of the population in the world is measured in million. So we write down in this way. Now, the pattern of the data points here suggests an exponential growth. This shape is like an exponential growth. So we may try to use exponential regression, and here you may consider this regression as a representation. So we try to find the exponential function fitting the data points best. So that is the subject of exponential regression, to find a model of the form. So that is 8 times b to the t. For this problem, we have to find a and b. And here, t is time, and that is corresponding to 1900. Okay. To solve the problem, here, now p is 8 times bt. Then we take both sides logarithm. Once we try to solve this problem, then now it's a little bit complicated, so that we may transform this problem into logarithm space. Then left-hand side is logarithm p, and right-hand side is now logarithm a plus. Okay, by using logarithm law, we can get that one. And that is now we define this one alpha, and we let this one to be beta. Then logarithm p is same as alpha plus t beta. So here, for each t, 0, 10, and so on, for each t, and for each p over there, we can write equation in this way. Now alpha, when t equals 0, and right side over there must be logarithm 1650, and once t is 10, then alpha plus 10 beta equal logarithm 1750, and so on, so that when t is 110, now right side must be logarithm here 6870. From these equations, now we can get an algebraic system we try to collect here 1, 0, 1, 10, 1, 20, and so on, so that will become A, and two unknowns alpha and beta, and then right side we collect these values to make a column vector. Once we can solve this algebraic system, and so that the misfit is minimized, and by using so the least squares formulation, if we solve the problem, then after finding the best fitting alpha and beta, and we may try to recover A and B. Here alpha is a logarithm A, so the A is exponential of alpha, and also B must be exponential of beta, right? So we can do that. Here, let's see program. So data is given, that is t values, and the second column is p values. And here, now we open array, the same size as the number of data points, and so that it's 1. So in the beginning, every the two columns are the value 1, and then the second column is changed by time, so that in the first column will be 1 and second column will be time. So we are collecting A here, and now R is the here p values along with the logarithm. So R. So we finished that algebraic system, and to solve it, we can use the normal equation technique, so that here the P is a vector of alpha and beta, that is A transpose A inverse times A transpose R. So the first component will be alpha, second component will be beta, and their exponential values must be A and B respectively. Now after getting A and B, we try to make now the plot by using time, and here I times B to the t. Okay, then we can see over there the pointed values, scatter plot, and the curve, best fitting the curve, and the actual value of A and B are given in this way. And then now here, so that the exponential model for population growth is given in this way. Okay, the unit is million, so that 10 to 3 is changed into 10 to 9, and b to the t. So as you can see over there, the curve is fitting the data points quite nicely. We'll see later on such computation in detail. Okay, here we will consider what the number E is. Here now E is chosen in this way among y called ax, and y called ax, a to the x is now when x equals 0, the value is 1. So for example, y equals 2 to the x, then now here the slope at the point is now less than 1. Now if we consider now y equals 3 to the x, then this function is passing this point along with the slope larger than 1 plus 1. Now the question is, what is the value of a such that here the slope at the point is exactly 1? And here the Euler here named the number, so that, and for the number e, and e to the x is passing this point along with the slope 1. So E is defined that way. So E is the quantity so that y equal e to the x is crossing y-axis with slope 1. So it turns out to be here 2.718282, and it's irrational number, and we can compute this one quite easily. Anyway, here that is E. Here E can be found as a limit. E can be calculated as the limit. E is now here the limit x approaches 0, 1 plus x to the 1 over x. Let's try to check how it is converging here. In fact, here we'll print out En, that is an increasing sequence, and we try to print out 8 values, and here x is now 1 over 10 to the n, and it's moving from 1 to n, so that first one will be 1 over 10, second one will be 1 over 100, third one will be 1 over 1000, and so on. So we are trying to choose 8 values that gradually becoming smaller. For that x, here 1 plus x to the 1 over x is computed, and we print out here, so that En is now, so that n value over there, and En, this value will be printed out as in this one. So the n is moving from 1 to 8, and you can see here now the quantity as x approaches 0, you can see that the value is approaching to E. That is, and anyway, these values are increasing, and here converting to E. So the E is 2.7182 something, is yet increasing. Okay. Now that's a computation check for E, but E is defined here so that y equal e to the x. The graph is passing the y-axis with slope 1. Okay, this is the first part of the section. Thank you.